Thank you. Good morning. Yeah, I want to update you a little bit on what Google Quantum AI has been up to lately. I think we all share a similar mission here in this room, and that is make quantum computing a useful technology for otherwise unsolvable problems. And the way how we want to get there at Google is we formulated a roadmap. You may have seen it if you followed our work. We published it a number of years ago, like around 2020, early 2020. And this roadmap shows essentially 6 salient steps how we envision to get to a useful machine, which we somewhat arbitrarily peg at a machine with 1,000 well-protected logical qubits. And with today's error correction techniques, let's pick surface code. We heard there are other choices, of course. It's roughly 1,000 to 1. So you would need to get to a 1 million physical qubit machine. So on our roadmap, we are now roughly at the halfway point. We are ahead of what we call milestone 3. That is 1 well-protected logical qubit protected to an error rate of 1 in a million. And I will tell you a little bit how we made a nice step in this direction. And of course, the hardware roadmap is associated or should be associated with an applications roadmap. And here we are ahead of business milestone 2, as we call it. That is the first useful beyond classical application. So with this, looking back a little bit, is our processor journey. So we have a rather artsy team, and we have this art theme going through. If you visit our labs and look at the decorations, how it looks, it's essentially, we often say we want to compute like nature computes. So it's this nature theme, and our processors accordingly are named by plants: foxtail, bristlecone, sycamore. I'm sure you have heard about sycamore. That was the processor line that was with us over the last few years and carried us through milestones 1 and 2. But now on route to milestone 3, I'm happy to introduce, on behalf of all our team, and it was a lot of work, want to introduce Willow, a new processor line. And this processor line, I will tell you a little bit what the specs are. So in some ways, it's a direct continuation of the previous ones. It's a 2D architecture, a square grid. So modulo boundary effects, you have a nearest neighbor square lattice architecture. We are now above 100 qubits. So to be precise, it has 105 qubits chips. It has tunable couplers. And what we are most proud of is the error rates in this chip across the whole system are very low. So it's a system engineering effort we are pursuing because, as you know, to do things like error correction, it only works if really all components are quite good or good enough below threshold. And one nice thing that has happened with Willow is while our team historically has always, I just said it, paid a premium to system integration and system engineering, historically, compared to other organizations, we didn't used to have the very best coherence times. But that has changed. So over the last year, our coherence times, our T1 times, shot up by a factor of 5. And actually in the lab, it's already way above this. So you may wonder what happened. Actually, many things happened. One thing I can share is that we opened a new, or have it fully functional now, a new in-house fabrication. So we have a fab that was from the scratch built up to build superconducting electronics. And there are only a few fabs like this in the world, and that's, of course, enormously helpful to beef up your quality and lower the error rates. So here in this sheet, there are you see sort of more detailed specs. And those specs, we have, of course, more than one chip, and we use the different chips in different experiments. But there are maybe a few things to call out. One is the all-important 2-qubit gate error rate. So if you look on the right side, so this is now slowly approaching, in median, I should say. It's not best, but in median, it's approaching 1 in 1,000. The long T1 times are already mentioned. But what's also important is that overall, that's the nice thing about superconducting architectures, they are fast. So we can do almost 1 million cycles per second. And actually, such systems that can be initialized very fast, where you have a high shot rate, where you can do tens of thousands of experiments per second, that is very important for algorithm development. Actually, this is just a preview to develop the first useful algorithms. Over the last 12 months, we have run 1 trillion shots, so 1 trillion experiments to develop new algorithms. And that's important because in any field or in software engineering, it is typically never the case that a great algorithm just falls from the sky and you run it. You have to, it typically has parameters, you have to tweak it, experiment with it, and that really only works if you can try a lot, or at least that helps. Yeah? So the two other key numbers is at the very bottom row, application performance. I will tell you about our error suppression factor lambda that became larger than 2 now, and I will also talk about the fidelity, or rather the time it takes to do random circuit sampling benchmarking on this new Willow chip. So, of course, median values are not the entire story. It matters if there's sort of a long tail distribution towards, let's say, higher error probabilities that can actually screw up the overall system performance. So therefore, here a quick glimpse at the distribution, the cumulative distributions of our error probabilities. So Willow was used to do 2, well, we'd like to call it breakthrough, or more modestly, important computations, benchmark results. Let me talk about the first one, that is a demonstration of quantum error correction below the surface code threshold. So I think everybody here in this room knows how quantum error correction works. You orchestrate larger arrays or groups of physical qubits into a well-protected, better protected logical qubit. It's the time-honored technique in engineering. You introduce redundancy to increase your safety or reliability. And then here it shows in more detail how we did this. We use surface code, information architecture, and then go from a 3x3 array of data qubits to a 5x5 to a 7x7. And then as we went larger in code distance, we went each time down by a factor of 2 in logical error rate. So that confidently shows an exponential reduction of logical error rate. So in some ways, I would brag here at this point and say, this is the most convincing prototype of a logical qubit built to date. And here you see sort of the money shot of our recent Nature publications that appeared yesterday. And what you can see in this plot is a number of things. First of all, if you look at these gray and black lines, this was our milestone 2. For the first time, as we went from code distance 3 to 5, the error didn't go up anymore. It came down, but only down by a hair, a few percent. So we said we are past the break-even point. But then since then, just in 1 year, now the error has come down much more significantly, and the reduction is not 4% anymore, but it's a factor 2. in each step, actually above, slightly above a factor 2. So it's clearly showing it's what in error correction is called below threshold. And the other thing, even though that was achieved before, we are also beyond break even. That means that the logical qubits are better than our individual physical qubits. That, of course, gratifying to achieve that. And then here's a plot. Looks a little bit boring, but I'm very proud of this plot, or my heart is a little bit into it, because a few years ago, I took this plot to our CFO when we were discussing budgets for our effort, and I told her, hey, please track us. What we are going to do over the next few years is we increase quantity and quality. We increase the quantity of our qubits, but we also increase the quality of all components, again, system engineering on our chip. And then you can watch us like skate down the endpoints of this slide. So each curve shows what happens for a given chip as you increase the number of qubits in your logical qubit. So you see our milestone 2. You may not even see it by bare eye. We got down, again, by a hair, few percent. But then the latest experiment, we went down much steeper, stated already, factor 2 each step. And so this came true as a prediction pretty much exactly on time and with exactly the specs we had promised. So in the last days, I was asked a lot by reporters, hey, is quantum computing like fusion? It's amazing, but always 20 years out. I say, no, it's not at all like this. There is a roadmap. There are dates associated to the roadmap, and we are pretty much tracking these dates with very little delay so far. And oh, I like this. Actually, Michael Newman, who is here in the audience, he made this graphics, which I like. You know, you can see right now we are here. You can see Sycamore and Willow on the left. You know, the 5x5 array, and then going to a 7x7 array. And he put the realistic rate where sort of error syndromes fire, and you see. It's much denser in the earlier chips, and then as we want to travel into the future, these they light up much less. So you have a lower density of error syndromes. Of course, will make it easier to decode. If they're low enough, you can almost decode by eye, which is of course a good thing, because that's another thing we did in this experimentation. We went down, we did real-time decoding, so keeping up with your quantum circuit. So let me jump to the second breakthrough we did on this chip. That is, we went back to our standard benchmark. I think by now, many organizations across the industry use random circuit sampling as a benchmark to compare different quantum processors to each other, or compare quantum processors to classical processors. And this was our 2019 experiment where we showed for the first time that our then Sycamore 1 chip could do in minutes what the then best supercomputer would have taken using the then best classical software to execute this benchmark as well. But then, as you may all recall, what happened then, there was a little bit of a red team, blue team dynamic. People were saying, oh, instead of using a huge amount of time, why don't you use a huge amount of memory instead? Or, hey, you haven't checked my latest improvements to tensor network methods. All these arguments were accurate. And however, it's of course easier to say than do. So it still took years then for this 10,000 year number to slowly whittle down. But as it whittles down, or whittled down, our processor improved. And when we rerun the latest form of this benchmark, of course, in every year, you run it with the maximum number of qubits you can do it with in that year. And of course, using the best gates, you can calibrate and tune up. So it shot up to this incredible time, 10 septillion years, so 10 to the 25 years. You can tell our marketing team helped me make this slide, so that's why it's put like this. So the maybe more scientific way of looking at this is in this chart. So we had predicted this already in 2019, that if you put an exponential algorithmic advantage on top of an exponential Moore's law type improvement of the base hardware, then you get a double exponential. And going from 10,000 years in 2019 to 10 to the 25 years shows that this is indeed happening. And also here you see ranges for each year. So these ranges come if you make different assumptions on memory. For example, we said, what if you had infinite memory and you had infinite bandwidth to access it? It would still take you 1/3 of a billion years to do it. But as soon as you go to realistic assumptions, it shoots up to 10 to the 25. So one thing we have never made bones of, random circuit sampling is not a problem that people on Main Street have. So it's not useful yet. But of course, it's still, in my book, it's the entrance ticket. If you cannot win on at least one problem, you won't win on a useful problem either. So you have to show this first before you can attempt the second. So now, again, looking at the roadmap again, something we are very eager to show it's possible with the new hardware platform Willow is that we can do beyond classical useful algorithms. So that's the next challenge for us, and probably for the community as a whole. Should state that so far nobody has achieved that yet. But what is less known, maybe to people in this room, not really news, but sometimes again talking, let's say, to the press, it's helpful to emphasize that, look, the chips we had over the last years, Sycamore and recently Willow, we could use them, or we did use them, to do or make good on Feynman's dream, to simulate interesting quantum systems. So essentially, we made interesting quantum states and studied their properties. And that led to dozens of publications in high-impact journals, and was from time crystals to non-abelian onions to traversable wormholes. A lot of interesting physics was studied and discovered. And we made actual discoveries. So we found, for example, the 1D Heisenberg chain was misclassified in which universality class condensed matter physicists thought it was. Or we saw in a magnetic system that there was a deviation from the Kibble-Zurich mechanism. So actual discoveries were made, small discoveries that in our team we nicknamed them discoverinos. But in hindsight, all of these simulations you could have done still on classical machines. So with this, now what we have is, on the one hand, we have only useful for benchmarking applications such as random circuit sampling, well above what classical machines can do. We have, in the axis of utility, we have useful quantum algorithms, but they could still be done on classical machines. So the challenge is to push now in the upper right quadrant on this figure. And again, I want to state that nobody has done this so far, and I would urge the community a little bit that if you claim you did something useful and beyond classical, please just don't compare against brute force, compare against something smart. Now, you should really compare it against the best, or at least pretty good classical method to make a confident claim, look here, was a useful algorithm and it was beyond classical. So looking a little bit ahead, what we could do with a fault-tolerant machine at the end, we have done a lot of studies that are of the nature where you work, let's say, with a pharmaceutical company, and they want to know, at what point in time does quantum computing become relevant to me? So we worked with them to costing it out. So let's say to simulate the enzyme P450, you may or may not know, about 75% of all small drug molecules get metabolized by P450. So it's important to understand it. And then we work to determine how many qubits and how many gates do you need to simulate this. And then we had similar collaborations with a variety of organizations. And I want to maybe pull one thing out because it's dear to my heart as a former AI machine learning person. That is the question, how much can quantum resources accelerate optimization? We know it's always a quadratical scale up, but sometimes it could even be an exponential speed up. And our team, a group of our team led by Stephen Jordan, have come up with a new algorithm we call decoded quantum interference. And this excitingly promises to deliver exponential speed up on certain classes of optimization problems. And the way this algorithm works, it establishes a duality between optimization problems on the one hand and decoding problems on the other hand. So the hope is that whenever you map or you're able to use sort of this quantum transform to map your optimization problem onto a decoding problem, let's say like Reed-Solomon codes, which we know how to handle well, then you may get an advantage on your optimization problem. And that indeed seems to bear out. And here I want to call out the nice public service that Scott Aronson did. He called this algorithm out on his blog and say, okay, community, let's try to dequantize it because we don't have full proof. Actually, this has changed. We do have proof that this works exponentially with an exponential advantage for certain corner case problems. But of course, we hope that this applies to broader sets of optimization problems. And how broad it is, we don't know yet. But the good news is that since Scott put out this call, the opposite of dequantization happened. Various groups, mathematicians, then joined and say, oh, we found a nice generalization, or have you thought about this? So there's plenty of new ideas that are coming. So we are just getting started, and there are now problems akin to polynomial interpolation that seem at this point to have this characteristic that there is an exponential speed up in optimization, which is of course a big deal if we want to impress our colleagues working in AI. And with this, I'm done. Thank you.